Yeah. Welcome back, everyone. Um, Next up is a workshop on quantum computing, breaking the Moore's law. And this one's being conducted by Nikhil Malhotra, Chief Innovation Officer at Tech Mahindra. This workshop will cover the history of quantum computing and its origins. We will also familiarize with the principles of modern quantum computing and understand quantum gates and quantum circuits. We'll also have a brief look at optimization using quantum annealing and also hands on with Qiskit tools and code practice for working with quantum computers. We will now invite Nikhil Malhotra to conduct the workshop.
Hi, Rucha.
Yes. Hi, Nikhil. The stage is all yours.
Thank you so much, Rucha. And let me just share the content. In the
Yes.
meanwhile, if, let's say, for example, my voice starts breaking or shaking up, I'll ask audiences to probably give me a sign, right? So let me know when you can see my screen and I can start.
Yes, we can see your screen now.
All right. Thank you so much, Rucha. And thank you for the
Thank you.
audience who's actually joined. Yeah, so I think there's a lot to unpack in about 55 minutes. I know I can't make justice to this topic, but what I'll try and do within this 55 minutes is the first half is try and debunk certain myths, understand why this decade is upon us, why every IT industry or technology industry needs to look at quantum computing, and what's the benefits of looking at it. Number two. Number three is maybe get into some core values of technology and debunk certain counterintuitiveness that this field brings in. It's a mammoth field. It has evolved over a period of last century or so. But I think this field is rightly upon us now as the fabric of computing slowly changes. Now, what I'm going to do is, before I actually get into this workshop, I'm going to give you some terms and glossary. Just remember these. You can, of course, refer to this particular, particular session later down the line. But first things first is the world that we live in, the world that is actually governed by Newtonian laws. This is the classical world. And this is the world that we normally see a lot of other Newtonian physics laws being applied. And this is the world which is an approximation. So if there is a word, let's say approximation, it might hit you. This is not the real world. It's basically an approximation of what we see within the universe. Of course, then there is a quantum world, a world which is based out of subatomic particles, the electrons, protons, and neutrons, which we're going to talk about in this particular workshop. You all know bits because you've been part and parcel of this particular industry growing through computers and transistors. And I would also tell you how Moore's law may not be effective in the coming 1 or 2 years. And that's the title of this particular talk. Then there's a world of qubit, which is essentially the bit in the subatomic world. And we'll tell you what this qubit is all about, how does it work, what are certain principles that really apply within the subatomic world as well. You all know classical computing. That's the world that you're living in. This includes all kinds of work that we do in terms of AIT, IoT, AI, cloud, Salesforce, so on and so forth. But we'll try and get into quantum computing, which is how do you make sure that you allow the universe to compute everything for yourself, which is the qubits, which is the subatomic structures. Now, I want to start off this session by this particular photo. This has been taken in 1927 Solvay conference. And this is the entire quantum mechanical mind or brain, as you may call it, people and scientists who've actually made sure what we're doing today is possible. You can see Madame Curie, you can see Einstein, you can see Rutherford, you can see Heisenberg, you can see Wolfgang Pauli, people you've studied in 12th, or let's say, for example, first undergraduate physics or undergraduate engineering courses, but people whose contribution have made it possible for us to understand what this field of quantum mechanics is. And this field has overgone a long period of change. So in the next few about 30-40 minutes or 45 minutes that we've got, I'll try and explain what this field is, how did it all start, a little bit of pop science as well, a little bit of history, before getting into the meat of how do you understand this field. I think it's it's counterintuitive as a field. B, in order to understand anything which is counterintuitive, I think for human beings, one possible way is to look at mathematics or to look at mathematical structures and formulate equations, because that's the only way that we understand the universe. The numbers tell us the story of the universe as well. So that is what we'll get into it. Now, one of the biggest triest for human beings have been, what are we made of? And this has been right there from the beginning of 18th, 19th century, right up till this point. It's the quest for indivisibility. You've actually studied this in 8th or 9th standard. You've also studied the first model of an atom. This was actually given by Thomson. It was called the very famous plum pudding or the watermelon model. And you also know that Thomson said that, the atom, or what we are all made up of, is a very tiny subatomic particle called an atomic structure, or an atom. This atom has is like a watermelon. It's got all around the red mush that you see in watermelon, which is the positively charged particles, and there are some sprucings of beads that you may find over there, which is the negatively charged electrons that are there. And these are beads that you may see in a watermelon result. Became very popular as the watermelon model. But we all know today, after reading science and after studying and after discoveries that happened in atom, this is not the real picture of how an atom looks like. But this was a good first attempt to explain what human beings are actually all made of. I I think you all know, and I'm assuming that all of you studied about Rutherford, and Rutherford's experiment was probably the first one to make us understand how an atom looks like. And this is just a representation of that same experiment that Rutherford did. I think Rutherford used a radioactive source of positively charged alpha particles, and he actually bombarded a gold foil with them. And what you saw was, or what he saw at a detector, which is shown by blue over here, is that most of the alpha particles would travel through the foil undeflected, which means they went straight, which also said that atom is mostly empty space, right? There's a lot of free space available in an atomic structure. What Rutherford then found out, that some of these particles obviously got deflected at a certain angle, and they were picked up by these detectors at the back end, which really meant that it seems that there's a positively charged nucleus, and that positively charged nucleus is actually deflecting these positively charged alpha particles, a concept which was of course known by and known at that time, because Maxwell and Lorentz are already shown that magnetic forces, in terms of north and north pole, would repel each other, north and south pole would attract each other. So it was very okay for Rutherford to understand, or to conclude that there is a positively charged structure in the middle of the atom. And of course, Rutherford did find one thing which was very interesting, that one, or maybe 0.001 percentage of those particles actually came ricocheting back when they hit something, and they actually got deflected at an angle of more than 160 degrees, almost at 180 degrees, which meant that there is something acutely positive and very heavy, which carries the entire mass of the atom as well, which was, of course, now we know the structure internally of an atom is positively charged, the protons, whereas the electrons are in orbitals and not in orbits that actually revolve around an atom. This particular experiment is actually called hard scattering. And later down the line, scientists did discover that there is obviously there's much more to reveal. If you actually bombard protons and protons, you would also be looking at quarks, which is something as the current theory or the standard model of physics today lies on. The weirdness in terms of all of this came when scientists started finding out, or discovering more about light. When I was studying quantum physics, or when I was looking at physics in general, it was clear that light had both properties of being weird and awesome, and it was really cool. Light behaved in both ways. Light behaved, and light behaved both in particles and wave structure. But I think the crux of it was actually made by Young's double slit experiment. Almost all of you would know this. I think, just for brevity's sake, I'm saying that Young took two different things, or took to two different mechanisms to test this. He actually made a kind of a slit structure over here, which you can see, and a double slit behind it, and a screen to record his observation when it came out from some of these slits. So at first experiment, Young's experiment was very simple to do with classical objects like a bullet. So he had a bullet sprayer, and the bullet sprayer was actually spraying bullets all over. So it was like a mechanically induced device which was spraying bullets. And when Young closed down one slit, let's say slit 2, and open slit 1, Young found that the probability distribution of those bullets came out to be like a normal bell curve, which we all know. This is a uniform probability distribution kind of a graph. We all know that these bullets would actually hit in at some place close to the slit, and they will normally reduce in intensity and also in frequency around these areas around the slit. Young also found that if he covered slit 2, and he opened slit 2, sorry, and he covered slit 1, he would find a similar pattern in slit 2 as well. And when he actually opened both of them, it was a combination of these two graphs that he found out. He also found something similar with light sources. He said if light sources, both slits are opened up, you would actually see patterns of light and dark coming at a screen. And this is an experiment that you all can easily do when you're actually sitting at home. Make a cardboard box, make two slits into it, open up a light torch, and you would see that at the back of the screen, or let's say on your wall, you would see patterns of light and dark, which is very clear, right? So waves normally do it. Waves, and you've seen these waves when you drop a pebble in a kind of a pond. If these waves come together constructively, like the crests and crests meet, they would actually double up and they would become light parts. If there is, let's say, a crest and trough that meets from a wave, they would cancel it out. That is the dark part of it. Clear, no problems. It was all very hunky dory at this point in time. So light was considered as a wave. Everything else around the world, which you see, is considered as a particle structure. So it was quite clear that science was moving in the right direction, unless or until at this point in time, Young did the same experiment with an electron. And he looked at, of course, there was a technique behind to find out an electron from a source and look at this gun as an electron sprayer rather than a bullet sprayer. Now, all of us also know that electron is like a particle, it's like a bullet, but of course, it's a particle at a subatomic structure or scale. And Young actually wanted to do this experiment with the double slit with this electron. So Young closes slit 2, opens slit 1, finds a very similar pattern. He was very happy. Particles are particles. They would follow a particular structure around slit 1, and they would actually, engulf or have themselves concentrated on this screen close to slit 1 with a probability, or with a uniform probability distribution around the slit 1. Do the same thing with slit 2. I think you find the same pattern. Young was very, very happy until Young opened up both slits. And suddenly he finds out that this electron, which he's considering as a particle, starts appearing as a wave like structure. So when Young closes, this experiment has been repeated by many, about hundreds and thousands of times. If I tell you, it again gives me those goosebumps over and over again, saying that this is the kind of the structure of universe that we live in. Something considered as a particle at some point in time, because the experiment meant it to be, suddenly becomes wave when the experiment changes and the particle starts behaving in exactly the same pattern as light behaves. It was as if the electron knew whether slit 1 or slit 2 was closed or both slits were open. Of course, now we know that this is attributed to the electron property, that everything, and this is a hint to something which I'll come later, everything on the plane that you sit today is actually sitting in terms of waves. When you try and catch those waves, they become particle. Now, I'll take an example of what you do. This is counterintuitive in nature. I can see you, you can see me, because somewhere or the other, our waves and wave functions are colliding with a lot of other things, and that's why we are seen. If we are not there and there's nothing to catch a wave function, we are as good as waves in the structure as well. And we are not just particles. So you only formulate a particle when you catch a wave. And at that point in time, the particle may appear as particle, but when you leave it, it is at its own nascency. It's basically a kind of wave-like structure, a counterintuitive principle, but Young's double slit experiment did tell us this. I think there was another guy who was working in the barracks at the same time, and he was bemused with another kind of an experiment which was done. And at that point in time, there was one principle which was constantly affecting scientists, and what was that if you shine light on a piece of metal, you would see that different kinds of colors may emerge out of those metals, which also indicated different kinds of emitted electrons, or the number of emitted electrons. That's first, because people always thought light as a wave. People thought that, of course, the intensity of the wave is related to, let's say, the amount of electrons that you emit. So if you take the wave source or the light source away, you would have lesser electrons emitting. If you bring the light source closer to the metal, you will have more electrons emitting. Of course, we know that nothing of this happened. This was told by Einstein that by definition, light is an electromagnetic wave. By definition, light is some ripples in the format of the universe. But light also, in certain cases, behaves as discrete packets of energy, which are called photons. And these photons have a frequency, they have an energy which is related to what we know as a simple formula that we now know: E is equal to lambda nu, lambda being the wavelength of energy and nu being the frequency. So, depending on the frequency, the energy of the emitted electrons really depends on the frequency of light which is emitting on them, which making sure that again there was a ripple in the field of saying that, look, light or in general universal structure behaves in two ways. If you don't look at it, if you don't measure it, it continues to behave as wave or fields of energy. And if you try and pick it and try and see it, it suddenly becomes a particle, and that particle has certain properties attached to it which we would utilize it, right? And these are the basics of quantum mechanics, and this becomes the basis of quantum computing. It's kind of probabilistic, but this probabilistic theory is probably the best theory to explain almost all mechanisms in the nature that you see. And this probabilistic theory is now coming in terms of computing, which we are actually going to talk about. So, a little bit of history was absolutely necessary for you to say that these are things that have happened over the period of time. This is a fun fact. I have a good friend who's actually working with LHC, and he sent me this photograph. And, and this has been proven time and again, but he says, look, we actually bring big rings around Central Europe, and we actually make protons move at very fast speeds, and we allow protons to collide. When these protons, when they collide, they obviously come out with some nascent particles which are formulations of the universe. So we try and observe them, and we try and recreate these stories about Big Bang. But right at the time when these particles are actually colliding, they've actually taken a photograph. It actually looks, the whole structure appears liquid. That liquid structure is now named as gluon plasma or a Rick fireball, which indicates the same theory that when you are not measuring anything at the basal effect of the structure of universe, it's all a wave of energy. But when you actually when you actually measure them and meet them, or catch them, suddenly you become a kind of particle, which is the kind of duality that you do. And it's funny, the liquid only stays for a period of time. If you could imagine the time taken by light to cross a coffee cup, and that's the only time that it takes for a thermal equilibrium. So it's very, very minute. It's about nanosecond scale, but yet scientists have able to confirm this facet that the universe does behave in this way. So let's go ahead. Now we come to the part of quantum computing. Why should we be excited? Number one, it's no longer science fiction. Practical use cases have started emerging. There are hundreds of fields that you would see, right from banking and financial services, to augmenting AI, to quantum machine learning, to even simulations. I think the last lecture would have been something around digital twins, which I was seeing on the stage. So digital twins, in terms of digital twins of really chemical formulas, structure, protein analysis, and so on and so forth. Large number of use cases have started emerging. India as a field now have about 8 to 10 startups, if I'm not wrong, who are working on this particular field in order to produce something, as a use case for practical purposes. Number two, obviously, there are complex scope problems in society. We have not yet sorted out all of them. First problem that remains for all of us is the technique of optimization. Even though we've got AI, and AI does significantly better in terms of optimization, AI is also constrained by the amount of feature set that it can take, for optimization for large spaces. And when I say large spaces, let's assume protein foldings, right? These proteins are basically structures that give body almost everything. Your entire functionality in your body is because of a protein, and proteins behave in a fashion because they fold in 3D space in a certain way. So their structure defines their composition and also their function. Um, if we are talking about medicine, if we are talking about medicinal facets, shouldn't we be looking at how these proteins fold and maybe able to simulate them? I think that's one of those complex problems which has not been solved by supercomputers as well. So that's where these computational requirements are asking us to go over there in the field of quantum mechanics. This is my prediction, but I think that's why the title of this slide, that we will see that edges of classical computing will be reached. And I think when I say edges of classical computing, I'm not saying that computers would not be formulated now. What I'm saying is that VLSI chips, or the kind of large scale integration that you would see in chips, would fail to happen after a certain point in time, which is 2024-25, which is my prediction. And there's a reason for it. I'll come back to this reason later down the line. The fourth problem is that global dependency on energy is becoming unsustainable. We all need energy for doing tasks, whether it's about with machines or whether it's a human operation. But mostly that energy facet that we are essentially using today is an irreversible operation. We need more reversibility in the whole environment to make it much more sustainable. Let me tell you one thing, and I'll show you by mathematics as well. quantum computing by definition only accrues reversible operation. If you're looking at your own transistor, if you're looking at working on your own computer, they're mostly irreversible operations. I don't think I've seen any reversible operation as yet. All we do is we actually do CRUD operations: create, read, update, and delete. We actually use a kind of memory bank, which we call as database registers. We actually store information over there. We take that information and we fire requests which actually go only in one direction or one line. It's not possible for us to reverse this operation back. Whereas quantum computing or quantum systems, by definition, accrue to the facet of reversibility, and that is something that I would show you in some formats over there. So again, starting with common sense, I think we all know that a bulb or a light switch can be both on and off. Well, the quantum world, since everything is a wave, it's somewhere there and somewhere not there. There are intermediate states that we can pick up. So when we say that the switch is both on and off at the same time, we are not really belaboring that point of non-intuitiveness. We're saying this does really happen in the subatomic world, which really means is there are light switches both on and off at the same time. A bulb can be both switched on and switched off at the same time. And that gives us that immense power of compute, because if you have only one bit available in the classical world, it can be either 0 or 1. But in the quantum world, it can be both 0 and 1. And when I say this term, both 0 and 1, it is somewhere in the middle as a linear combination of both 0 and 1. And when we say that, we are actually utilizing the power of the bit to 2 times, which is 2 raised to power 1. If you continue this with n bits, you have 2 raised to power n such qubits or bits that are available in the quantum world for you to work across, which gives you at a whisper at the power of computing that you have over this period of time. What I'm showcasing you is essentially my risk that may come in with quantum is something over here, which is I'm showcasing you my RSA key. RSA works on a very simple factoring algorithm, which says if you've got the number 48 equal to A into B, if you've got 48, figure out A and B. Well, with simple, small little examples, it's possible. If I give you 48 equal to A into B as equation, A and B could be either 8 or 6, 6 or 8, 12 to 12 or 4, 4 or 12, so on and so forth. I think a brute force of a machine is good enough to actually break this factorization. Whereas in RSA, the modulus of the kind of keys that we are using have about 2056 bits. In order to break this kind of a system, right? So 2056 bits equal to A and B, and if you have to factor A and B because those are the keys, you would take a normal computer would take about 4 quadrillion years, which is 1.5 times the life of the universe. The fastest supercomputer takes about 1.5 billion years. But lo and behold, a quantum computer in a synthetic scenario has actually broken this key in hundreds of seconds. So security or post-quantum cryptography, or cryptography as we knew it, is bound to change in the coming years because there's something available with us where we can use the power of the universe to actually do a large number of parallel computation, right? So that's some of the other things that we need to understand in terms of security when we're looking at quantum. Now, I'm just going to give you the back end. So when we say is the classical bit, you are essentially considering the bits in a silicon and you're saying we can store information as either 1 or 0. This either 1 or 0 is basically the voltage that you give to the transistor, which is either going to be 0 volt or 5 volts. In quantum, however, these bits are represented in a very different fashion, and this was given to us by Dirac. This is called the Dirac vector notation or Ket notation, where you see this kind of a bracket over there, a line and a kind of greater than sign. And what we are seeing over here is that Ket 0 is 0 state or 0 bit, and Ket 1 is 1 bit, but we call them as qubits because they're quantum. And they're also represented in a very different way. So Ket 0 is represented by two things. It's not represented by one. In the classical world, 0 is 0. But Ket 0 in the quantum world is actually represented as a vector of 1, 0. You can also think about it or remember this saying that the 0th position of the array is 1 and the first position of array is actually 0. So that means Ket 0. Ket 1, on the other hand, is represented quite the reverse. It's represented 0, 1 in as same as a vector, but you can remember it saying that the first position of the array is 1. 100% that this is the vector 1 or the Ket 1 state. and the zeroth position is 0. So that's one of the easy ways to remember how ket 0 and ket 1 are. And these are the basis states, right? The other thing is that they are also vectors which are orthogonal in nature. For those of you who are math nerds, orthogonality really means that there is a 90-degree separation between these two vectors. So if you do a kind of inner product between these two vectors, they would always be 0. The other thing is the normality part, which we say that if you do an inner product of a vector with itself, which is 0 and 0 together, you will obviously get 1. So these vectors are also called orthonormal vectors. For folks who are trying to get into this field, for folks who are actually looking to go deeper, because this is a field that has just started, I've just written a very blue box structure over here called the vector spaces. And these vector spaces need to be understood before you get into the world of quantum computing. And vector space is so vast and so huge that it is not possible for us to cover even with 3 months of lecture systems as well. So but the idea behind vector spaces is very simple. The idea is that these are spaces which include set of vectors which behave in a separate, a special way. And everything, for people who just want to get to and skim to the part of what quantum computing is, everything in quantum is based out of linear systems and linear equations. So that's the vector space that we actually look at, which we only look at linearity in the system, right? So simplistically speaking, now 1 bit in the quantum world means 2 possible combinations, 2 raised to power 1. 2 qubits or 2 bits in the quantum world mean 4 possible combinations, which is 2 raised to power 2, and 3 qubits means 8 as well. So if I sum this up pretty quickly, you live in two worlds. One's the classical world, one's the subatomic world. The subatomic world behaves as both wave and particle in a dual fashion. Unless you measure something in the subatomic world, it'll continue to be in multiple states. And I don't want to get into a conversation of multiple universes, even though that is true. And when measured, and that's an important, interesting point, the fourth point, when measured, a particle or any system can be in that state of multiple states and multiple universes in the subatomic world. But when you try and measure them, right? So, for example, if you try and catch them, there is only one state that they may come out, and that state is either 0 or that state is 1, which is very interesting because we need answers to understand in our own classical way. We don't need answers to go in an atomic world because that's the world that we don't know. We can give the atomic world the calculations to calculate, right, in a bigger way. They can take all the kind of forces that they want to do to calculate, but when they come back to us, it has to be either 0 or either 1. So we use the subatomic world to improve the calculations as well. Now, quelling again some myths about quantum, which I've already been doing. Number one, general anachronism is it's too arcane, too far off, it's for academics and theorists. I think that's not true. A lot of young kids are now, and a lot of university graduates are now working on quantum computing and different parts of quantum. Quantum computing is just one part of it. There's quantum sensing, there's quantum security, there's quantum communication, so many other different fields in which you could do. And the reality, however, is that we need, for some problem solving, and you'd be surprised at some of these problems that you want to solve, optimization of, let's say, group of people that is sitting in your classroom or sitting with you. If there are 15 to 20 people sitting with you, and I want you to arrange in terms of features like their caste, color, creed, sex, gender, so on and so forth, the combinations can become so huge that you would not be able to solve even with a supercomputer. And that is some generic problems that we face today in the classical world, for which quantum has come in. Also, a large number of use cases have started coming in between combinations of AI, in quantum computing and giving it onto the cloud. This is also the emergence of a new business model as we actually see it. Okay, so let's get into some basic, structures of quantum computing and quantum principles, since it's a kind of workshop. So I've told you about the first principle on the left. That principle, by definition, is called superposition, but that means exactly the same thing that I've been talking to you up till now, which is bits in the classical world can be either 0 and 1. In quantum, there are linear combination of both 0 and 1. And that's why you can actually use the power of both to compute and calculate. And that's superposition. The second part, which you see over here, which is entanglement, is very, very spooky. And that is got, and there's a huge loads of books over there. I think there's a huge amount of theories. I think the standard model of physics has also come because of the quantum field theory over here. But this is where things get very, very interesting in terms of what quantum computations can do. And this field is, this principle is called entanglement. Typically what happens is, and let's consider two particles in nature. One is with spin up, which is shown in blue, and one is in spin down, which is in red. These particles sometimes come together and they formulate a kind of system which we call themselves as they being entangled. Now what does the meaning of entanglement means? These particles behave as one. So if I take this blue part, they're still separate, but they're behaving as one system. So if I take this blue particle and put one in my pocket, and I asked somebody, an astronomer, to take the red particle and send it across a spaceship on NASA, or whatever we have in ISRO, and send it to outer space. These two particles still formulate themselves as one common system. So what happens really is, if I measure something on particle which is blue in my pocket, at that very instant and that very millisecond or nanosecond or microsecond or whatever you may call it, the particle red would also show that same measurement, or something which is diverse. Now this is spooky because Einstein termed it as spooky, because it's belying the behavior of space time and the speed of light. By definition, which was given by general theory of relativity in Einstein, or by Einstein, it was that light, there's nothing more faster than the speed of light. The speed of light is constant. It is kept at 3 into 10 to power 8 meters per second. But this theory is belying that principle. How can information, or how can this system become so unique, where we do not know the individual parts, but we know the sum of parts, which is we know the whole system? Let me tell you this. Let us assume that these two are two coins that you are actually flinging up in thin air, and a coin can be either heads or tails. So there's 50% probability the blue one can be either head or tail, and the red one can be head or tail. So we do not know whether each one of them is true or not, right? So we don't know the probability. It's a 50% probable chance that when we flip the coin blue, it'll come as head or tail. So we don't know what that system is, but we know this for sure, that if blue turned out to be head, red would instantly turn out to be tails or heads or whatever the state may be. So we know the complete system, we know the full system structure, even though the individual parts are still probable. This is so unique, and this is so disconcerting and non intuitive, that Einstein spent his entire life trying to debunk quantum entanglement, to say this would not happen. And this shouldn't happen, even though we've now proven with experiments that it does happen over long distances. And the technique, this particular technique, is being now used for quantum security, for securing keys, and carrying signatures of these systems. Like, for example, if blue is on my part and I have kept it on my server, and red is a packet that I'm sending with my keys, which are traveling over a wire. If a hacker wants to attack these red keys, the moment he measures or attacks them or finds out, I have an instant message that goes into blue system, that somebody is trying to look at the keys, and I can change that instantly, because that information travels faster than the speed of light. Right. So this is the counterintuitive nature. There's another third one as a counterintuitive nature, and this is this is in order to explain this, and if you look at the diagram, I'll explain it in a different way. All of us have played cricket with tennis balls during our lifetime. What happens when you throw a tennis ball against a glass window? I think two things happen, right? We have seen this thing happen in our lifetime as well. Either the ball breaks the window and goes to the other side, or the ball bounces back from the window and comes to my side. Never ever have you seen the ball cross the window, come on the other side, and not break the window as well. Well, this is another counterintuitive nature of quantum mechanics. Because everything is a wave, there is a probability, a minor probability though, but there is a probability in which some particle that you're throwing, or a ball that you're throwing across a barrier, even though it does not have enough kinetic energy to cross the barrier, it may come to the other side of the barrier, because it was always a wave. And I've actually shown a kind of video over here. This is a real experiment run in the lab. An electron is actually bombarded against the wall, and you would see a portion of the electron comes on the other side of the wall as well. And this is a very hard scattering wall. It does not allow the electron to change, but this particular experiment shows this tunneling nature, where the electron can tunnel through this wall and come on the other side as well. This is another counterintuitive nature, which is called tunneling. This helps us as one of those principles of finding out or reaching the gradient descent, or countering the gradient descent, and getting to the optimum or local optimum much more faster. Because over here, We are not going through step by step gradient descent to reach to the bottom, to find our global minimum. We can actually tunnel through these walls and tunnel through these mountains, etc., if we may call it in that fashion, and reach to the optimization structure faster. But this is also the reason why I'm telling you why Moore's law will not hold in order to make sure that large VLSI chips get entangled in the near future. Because at this stage, small or very large scale integration devices, chips are being made at 5 micron sizes. The moment they go a little bit lower, this effect of quantum tunneling will start happening almost instantaneously. So if you've got pieces which are close to each other, electrons would start to tunnel from your circuit to another, and this will produce errors in the computing facet. And that's why my prediction that 2024-25 may see the end of Moore's law in terms of how we can pack large number of chips in small places, because these quantum effects or quantum tunneling effects which may start coming up, right? Okay, there are different parts of types of quantum computers. Some of them are called annealers. These are where they're restrictive, they're not general, but they are actually using a principle of physics, which is basically everything in the world will have will go down in energy, and that when you go down in energy, that is where the global optimum or optimize your optimized problem solution is. So it's basically used for more optimized systems or optimization problems, and there's a large number of them. There's a company called D-Wave which is actually building these annealers, and they've been produced in a lot of effects, and a lot of companies are using them. There's of course the universal quantums, which we say that we will actually make circuits like gates, because gates have been the traditional part of what we do in our normal computers. And this has become, some of the companies like Microsoft's, IBM's of the world, and Google's of the world are looking at universal quantum computers, which can actually give us true advantage in terms of what we are trying to see for solving some of these challenges that we're seeing, right? Now, these are two different images that I'm showcasing you. One of them is the D-Wave system. The other one is the IBM computer. That's the innards of the IBM quantum computer. Large number of gold quantum, copper wires. But then the chip is very minute and small. It actually sits right at the bottom. These systems are kept at a very, very low, at very, very low temperatures to minus 273 degrees Celsius, which is 0.015 Kelvin, which is even colder than the interstellar space. There's two reasons for it. If you look at the structure of material or atom in general, one thing which is bigger problem is noise, which is created by black body heat radiation. And as a result of that, we don't want these quantum qubits to decohere, and we want them to stay wherever they are if we've actually put some value on top of them and do that calculation for us. So that's why they are kept at very, very low temperatures. There are different ways of making quantum systems. IBM, for example, uses a transmon qubit system, which is a superconducting qubit. There are others who are using ion traps and so on and so forth. The important thing to realize, as I was mentioning, is this is also sustainable. The only thing that this processor generates is heat, or that's the only derivative that comes out of it, right? So I will not go into annealing, but I will give you just slight bit of a hint over there. And this term called the Hamiltonian, even though this term sounds a very, very very, very gimmicky, or it's very difficult to understand. The Hamiltonian simply means the description of a physical system in terms of energy, right? So it's a function in which I pass the physical state and it gives me out an energy, and that's what I need to know. So if you're looking at, let's say, an apple kept on a piece of wood or on a table, the Hamiltonian over there has high because it's got high potential energy. When you put that same apple under the table on the ground, then it's got low potential energy, so on and so forth. That's all it is actually trying to tell you. But the annealing facet is also being used by D-Wave systems to create these superposition states, which I've shown, which I would not go deeper into because we'll go into circuits more often than not, right? So this is our approach. We have actually looked at in different ways. We have actually looked at the trough of expectation. We're working on all of them. We're working in annealers, we're working in gate circuits. We are actually doing a lot of other work in terms of research. What is the applications today, right? And which is very important, which is why you are here. Before I get into the mathematics of it, the applications range from materials, where I told you it's very, EVs, alternative sources of EVs or batteries, etc., are very important at this point in time, and quantum's trying to solve that in terms of chemistry computations. Satellite placement. If you look at the lower Earth orbit today, it's actually riddled with a lot of satellites. So where do you place your satellite better? Or how do you even think about doing that, right? Logistics, finance, for example. Goldman Sachs as an organization has a huge team which is actually looking at portfolio optimization or fraud alerts in terms of quantum computations, right? And then there are other mechanisms which we do. I want to give you an idea of where it is being used. I think this was one of the first use cases by Volkswagen. And when Volkswagen used this quantum computer, they actually used it to do route planning and route optimization. And they were able to do it at about 1/10 of what they would have done had they used AI systems alone. So this was a combination of AI as well as quantum systems. Then there is another company called Denso. You might be knowing this. This is, of course, they have used quantum to actually reduce the amount of time that an automated guiding vehicle would take internally in their factories. And this was a 15% improvement that they did using quantum, because the kind of computations and the kind of, ifs, else, and buts, and also the kind of, the features that they wanted to do were too many for a classical system to solve. And as a result of that, they went into quantum. Another example of a company who's actually using it for genetics and genomic studies as well, because that's a space which involves a large amount of data and large feature spaces. Then again, this is a source from IBM, but they have actually given a lot of other things like airlines, BFSI, chemicals, healthcare, and life sciences, where you can look at these things. This is our work, and we are essentially looking at drug design. And drug design is essentially a very, very important area today, because number one, there are a lot of manual steps involved, which include target discovery, which includes finding out the binding sites, preparing a kind of molecule, trying to pick up molecules and put them together, and so on and so forth. And there are automated steps in AI where we can actually use how do you generate a kind of simulated molecule using GANs to discover drug candidates. But they take a lot of time, number one, and they are also kind of not really there because of the kind of space that they're looking at. So we actually use quantum in a big way in terms of looking at how this docking parameters and engines can actually be working out, right? So this is an example which I don't want to do that, right? So let me take you through the technology part. I think if you have to get into quantum computing, because it's a kind of workshop, first things first is to understand linear algebra and vector algebra very, very closely. And what I'm actually showcasing you over here is just a review of matrix multiplication. If you've done this matrix multiplication, great. I think what I'm showcasing over here is a 2 by 2 with 2 by 1. The result is what you know, it's about 2 by 1 matrix, a into x plus b into y. So that's one of the things that we have to be cleared of. So you should know matrix multiplication. Okay. Having said that, we also should know that there are four kinds of operations on a single bit. And when I say single bit, there's identity, of course, that I can actually have a kind of identity matrix applied on a single bit. When I say single bit, this is a qubit, 0. It yields actually 0 itself. And if I apply identity matrix on a 1, it will yield me qubit 1 or get 1 as well. There are also negation, which I can do this. There's also constant 0 and constant 1. Now, one of these operations or two of these operations are reversible and two are not. For example, if you look at constant 0, every time when you apply this constant 0, either on ket 0 or on ket 1, you will yield 0 only. This particular operation will always yield 0, whether the starting point was 1 or 0. So it becomes a kind of non-reversible thing. If I know the output, let's say the output is 0, I don't know how you started off with, whether you started with 1 or you started off with 0. Constant 1 is the same thing, whether you start with ket 0, ket 1, you don't know what the answer is. Whereas in negation, you know, if you reached 1, you must have started from 0. If you reach 0, you must have started from 1. Identity is exactly the same. You can actually reverse back this operation, right? So reversibility in terms means that given the output, I should be able to get the input as well. And this is what we have actually done. We say that identity and negation are reversible, but constant 0 and constant 1 are not reversible because you do not know how you started off with. By definition, all things done in quantum computation are actually their own inverses. So they are reversible. So if you apply in quantum computation that feature set or that behavior again, you will get the value again at the same point. Another interesting thing that you must know, where multiple qubits actually combine together, is the story of tensor product of vectors. This tensor product is normally represented by a cross sign and a circle. Now, what this tensor really means is that x0, x1 as a column vector is being combined by another column vector. Then it takes in the entire vector itself and adds it. So if this is 2 by 1 and this is 2 by 1, the resultant is actually a 4 by 1 vector, because you have this vector being taken by x0, so it becomes x0, y0, x0, y1, and this vector again being taken by x1. This tensor product really means that two qubits are aligned together when we actually make circuit. You can follow the same technique for a 3 qubit as well. So when you do 3 qubits, you will get 8 such values, which is also the whisper to the power of computing that you are essentially looking at. That if you've got 2 qubits, you can do 4 operations. These are 2 qubits, you can do 4 operations simultaneously. If you've got 3 qubits, you can do 8 operations simultaneously. This is how multiple qubits are represented. When you say multiple qubits, you actually represent the same two arrows, which is the line and an arrow, and you represent two values. This 0 0 basically means that 1 0 is being tensored with 1 0. Remember, 1 0 was ket 0 because 1 in the 0th position means 0 itself, right? And that's why we are saying, so you get 1 0 0 0. If you do 0 1, you will get this. If you have 1 0, you will get this state. If you have, let's say, 3 qubits, you will get an 8 state. So we call this a product state. We also call this a tensored representation. This also represents the value of a vector in 2 raised to power n structure. And that's why it's important, right? Now, what's the importance of doing all of this function? Why is matrix or mathematics important, you may ask? There are two things. Number one is that there are vectors. Vectors have always represented states of a system. So a qubit vector or a ket vector, as we call it as 1 0, represents a state of the system that says it is in state 0 or 1. Uh, if I want to change this state, I think the best way to change a state of a vector is by applying a matrix. These matrices have no special purpose. A lot of people, when I ask college students, they tell me matrix is an array, it's a structured system, it's a group of things. I don't think so. Matrices are basically a representation to change a vector. They are basically required to transform a vector, to mold it, to stretch it. And that's the main reason, because the vector really represents the state of the system. Now, these matrices form the gates. If you look at your AND, NAND, and NOR gate, which you see in normal computers, they are also like a normal matrix being applied to, let's say, a vector in real terms. In quantum computing, this becomes more pronounced because everything now is based on these gates. So the one gate that I'm actually showcasing you is called the C0 gate. The C0 gate is represented by this, but you see two things over here. You see that column number 3 and 4 have been flipped. If it was an identity matrix, it would have been the other way around. And this control not bit acts as an XOR gate, or similar to an XOR gate in terms of your the real life, or let's say a classical bit that you may call it. In the quantum world, the XOR gate for them is called the C0, which operates on multiple qubits over here. So if I have to apply a control not over 1 0, let's say, I will look at C, and 1 0 means that ket 1 will be tensored with ket 0. So which means that when ket 1 is tensored with ket 0, that means all of this will actually combine over here. So 0 times 1 is 0, 0 times 0 is 0, 1 times 1 is 1, 1 times 0 is 0. That becomes this state. And then I apply the C0 gate. If I apply the C0 gate over here, the net resultant that comes out to me is 1 1. Similarly, if I apply 1 1, it applies to 1 0. You can check out the remaining, whether you want to apply on 0 0 0 1. The important interesting thing over here is this is called a control knot. If the most significant bit of this qubit is 1, the other bit is flipped. If it's 1 0, it'll be flipped to 1 1. If it's 1 1, it'll be flipped to 1 0. And there's no rocket science over here. The rocket science lies basically in making that gate. If I was to look at this particular gate and only count the columns, this was 0 0 0 1 1 0 1 1. You can see 1 0 and 1 1 anyways being flipped internally within the matrix. So when it applies on the matrix as well, that is what happens. So if this one has the most significant bit, it will change the rest of the bit, right? So the interesting thing that I wanted to tell you was that there is a rule that we apply to find out what's the probability, and that's what comes in when we actually talk about superposition. So if, let's say, a qubit is represented by this a and b, 0 1 1 0, etc., the probability of them occurring at a certain point is actually given by Born rule, which is a square plus b square. So let's say, for example, if 1 0 is the qubit that I represented 0, this means that there is 100% probability that this qubit would lie down into 0. There's a 100% probability that this qubit would lie down into bit 1 when measured. Whereas look at this qubit, one half the probability that it will be 0, one half the probability that it will be 1. And since the probabilities always have to be 1, you can add them together and you can formulate 1, right? So what we are saying over here, over here it's 1/4 and 3/4 and so on and so forth, which means that you are somewhere in the middle of being both 0 and 1, which is entirely the effect of superposition that I told you was the facet that quantum computing would give you. This is one of the ways in actually you look at it. There's an interesting way which I'm actually showcasing. Luckily, I have IBM's Qubit and Qubit Lab. So this is what we do from making sure that this is happening. So, for example, this is where we actually import, and I'm actually using very simple Python codes over here. Give me a second. I'll just shift enter. So this is what you first, of course, import as library. So you can see that this is a Qiskit system. A Qiskit is basically a kind of language constructor and SDK given by IBM to actually make these circuits, and they can also give you how these circuits really perform each other. So what I'm showcasing you is basically the kind of things that you can do to invoke or import libraries. Now I'm going to do a simple rotation. So let's say this rotation is normally represented by this particular sphere, which is called the block sphere. The north pole always represents 0, and the south pole represents 1, and that is all what you need to know now. There is also x and y direction, which we won't go into. What I'm saying is, by simply using this formula called quantum circuit, I can start a circuit of a qubit, and I can simply shift that qubit to go from 1 to 0. So this qubit, when it starts, it's always 0, but I'm actually giving a kind of X gate, a NOT gate on the 0, which will just flip this bit to the one side. And the circuit can also be seen over here. Now, if I want it to become somewhere in between, right? It's neither 1 nor 0, and I want it to be in, let's say, half of that quantity. There's another gate which is called the Hadamard gate. If I apply that Hadamard gate, the bit would be somewhere in the middle, right? So it will be neither 0 nor 1, somewhere in the middle. And that's exactly what the next gate was I was trying to tell you, was the Hadamard gate. A Hadamard gate is used to actually create a superposition of qubits. So let's say if there's a qubit 0, I want to create a superposition so that it's, at this point, qubit 0 is represented by 1 0. When 1 0 is represented, it means it's 100% going to be 0 value, because 1 is the array point 0. But if I apply this gate on top of it, it will come into this stage, which means it's half there and half there, which is half there and half there. It's no longer either 0 or 1. This superposition is the phenomena which gives you that multiple amounts of power of computing that a quantum computer would do. Similarly, I can apply it on 1. So if I was to apply it to 1, let's say, for example, and I can just say that this qubit starts when you actually put this line called QC equal to quantum circuit 1, it basically makes a quantum circuit and puts it as qubit 0. I will just apply quantum circuit 0 over here, and I will just make it 1, and then apply Hadamard gate, and you'll see that it actually shifts to the other side, which becomes negative, which actually means why it is doing negative portion over here when Hadamard on 1 was applied. And this is exactly what we are doing over here. When we actually apply this system, it turns itself into Hadamard 1. But there are different ways in these quantum circuits can be applied. I'm just showcasing you one more quantum circuit. This is how a quantum circuit looks like. These are two qubits. This is given by Q0 and Q1 when you make the circuit. This is a classical line because you want to measure that circuit. In this scenario, what I've done is I've actually applied a Hadamard gate, a kind of NOT gate, and this sign, which is plus, and this system over here. This particular system is called the control NOT, which you just saw over there, which was nothing more than this control NOT that I was actually showcasing you right here. Sorry. This was control NOT. Now, this control NOT means that if you start with 1, and if you give 1 over here, or let's say you give the most significant 1, would it change the value of the other bit, right? And you can make a simple circuit like this, and you can try and measure the results that happens. And this is how you measure those results. You measure probabilities of how they come, so on and so forth. So, um, in essence, what I wanted to share with you, the idea was that Quantum computation is for there to connect with you, is there for you to actually look at a lot of things that are going on. There's a huge facet, it's a huge branch in terms of what we can look at, from purposes of what we are trying to solve. I've just scratched the surface. There is a lot more other things that we are actually looking at in terms of making circuits, putting up even techniques of artificial intelligence and machine learning onto a quantum plane, drawing these circuits again with gates. So, possibilities for a computer scientist or a computer engineer are many. Number one, linear algebra has to be clear, calculus has to be clear. You can just get into the branch of quantum physics, and quantum computation can start happening. I will stop here because there's less time available, but I can take in some of the questions that you, if you have.
Yeah. Thank you so much, Nikhil, for a powerful session. The feedback says it all. We have a couple of queries in the chat box. If you can answer them right away in the chat box,
Yeah,
and we also have some in the question and answer tab.
yeah, I'll just pick up few of them, right? So, for example, one of
All
the
right.
things that Kesh mentioned was use case for fintech world. I think fintech world is actually going through a big change in terms of quantum. Number one is, of course, what do you call, optimization of portfolios, and also fraud alerts is something that is happening within the quantum world. Again, what is the current state of quantum computing? Pradeep asked. I think it's pretty well advanced at this point, Pradeep. We don't have a production system. There are two ways in which quantum is going in. Number one is the annealing mechanism, and there are production use cases in the annealing system. What does annealing mean? Use the Hamiltonian of a physical system to drop down the energy, and that is where the optimized solution for your system may lie. So if you're trying to optimize something, the other one is the circuit part, which is what IBMs and others are doing. There's still a lot of work going on to reduce the amount of error rate in terms of decoherence of qubits. It's still there. We are still working out on some of these things, but it should come up in 3 or 4. Somebody said 2024-25 is an aggressive pipeline. Yes, it is. And that's what I do think, that by 2025, you would see semblance of effect of Moore's law going out. 2030 will be the decade when you will start quantum computations in a big way. But 25, you would see that chips will reach a certain value. They're at 5 microns or 5 nanometers or whatever you may call it. The moment you go lower down, quantum effects will start happening. Right? So,
All right. Thank you so much, Nikhil, for a powerful session. And we will now take you backstage, and you can answer further queries on the chat box.
sure.
All right. Thank you. Audience, allow us 2-3 minutes more to come up with the next session.